Photonic crystals are normally classified by their periodic structure. A one-dimensional photonic crystal has a periodic structure in one direction, while a two- or three-dimensional photonic crystal would have a periodic structure in two or three directions. One-dimensional photonic crystals were discovered in 1887, while two- and three-dimensional photonic crystals were not discovered until 1987. Photonic crystals are optical materials created by periodically stacking layers of elements with differing optical parameters. These periodic mediums are made of at least two materials having different dielectric constants, or epsilons. Photonic crystals utilize the existence of photonic band gaps that form from periodicity among materials to limit the propagation of light along certain wavelengths to produce desired effects. So, as shown in the figures, a photonic crystal can do as much as direct light along a certain path or even trap certain wavelengths. In principle, photonic crystals can be used wherever light is present and can be manipulated. More specifically, photonic crystals take advantage of the light reflected from the material. Photons enter the crystal and only certain frequencies reflect out due to periodicity. Photonic crystals only reflect certain wavelengths of light because of the photonic band gaps. Photonic band gaps are ranges of frequencies for which no wavelengths of light exists in a medium. Here we have a graph of wave number versus frequency for a non-photonic crystal with a uniform medium. By treating it like a periodic medium, we can fold the wave numbers over at a plus or minus pi over A. With this new folded graph, we can see the point of reflection at k equals pi over A. The positively sloped portion of the line around this point is represented by cosine of pi times x over A, while the negatively sloped portion is represented by sine of pi times x over A. With a uniform medium, both of these functions are equal to each other at k equals pi over A. However, once we add the periodicity of a photonic crystal, a gap forms between the upper part of the line, the sine function, and the lower part, the cosine function, because the two functions are no longer equal at pi over A, which, in turn, forms a gap which the frequencies no longer exist. The discovered properties of one-dimensional photonic crystals was then applied to two- and three-dimensional photonic crystals. There are several types of three-dimensional photonic crystals, the most common of which being wood-pile structure. Other types include spheres in a diamond lattice and inverse opals. The figure shows how photonic crystals may be applied in something like a fiber optic cable. By allowing only certain wavelengths of light through, the rest propagates along the length of the tube. Here are some more cross-sections of the most popular use of photonic crystals by man, fiber optic cables. Photonic crystals are also used in clothing, lighting, gift wrapping, makeup, and other eye-pleasing applications. In addition to man-made instances, photonic crystals also appear in nature. Shown here, you can see some different examples such as beetles, butterflies, or peacock feathers. Natural photonic crystals also appear in various stones, the most well known being opal.